Hey folks, I'm Mr. Hartzler here for Hartzler University, and I want to talk to you about trigonometric functions and acute angles. Let's go and get started with some examples. Well, actually some notes first. Alright, so trigonometric functions, they can sound scary, and sometimes they are, but for the most part, they're really not that bad. They're really just ratios. So it's one side compared to another side, and it works for right triangles, and it works for all triangles, but we're going to focus on the right triangles, at least at first. So these are the common ones that are up on your screen right now. Sine, cosine, and tangent. Sine is opposite over hypotenuse, and we're referring to the legs of the triangle when we talk about that. So our angle theta, that cool little letter in there, it's spelled, in case you want to ever write it, is Theta, theta. So if I look at this little picture in the bottom right corner, I have my theta, and from that spot, wherever that is located, opposite of it is all the way across the triangle. Adjacent just means next to. It's really just a fancy word for next to. Like my house is adjacent to my neighbor's house. So adjacent means next to. Okay, so it's right there. And then my hypotenuse, you know what that is, right? That's the slanting line. That's the longest leg of a triangle, or of a right triangle. And so that's what how these words come from, right? Opposite of wherever my angle is. Hypotenuse to my triangle. Cosine is adjacent over hypotenuse. And then tangent is opposite over adjacent. Tangent is also another thing. Tangent of my angle is also going to be the ratio of I don't know why I wrote sine of my angle over cosine of my angle. It's kind of neat that way. But that part we really don't focus on a whole lot. If you remember opposite over adjacent, you're probably good for the most part until you get to calculus. All right. There are some mnemonic devices because this can be challenging to remember all of this. They're big words. I get it. Over on the left, a lot of people just say so ka toa, just to help them remember. And they'll write at the top of their paper, so ka toa. There's a story about somebody getting their toe hurt by a cow. It's a whole thing. Look that up if you're interested. Another one that we have a calculus teacher here who uses this one a lot is some old horse caught another horse taking oats away. Right? If you put a space in there, then that helps, right? And it's the first letter of each of these. Some, or sine, old, or opposite in this case, horse, hypotenuse, caught, cosine, A is adjacent, H hypotenuse, tangent, opposite, adjacent. All right. Then another one that another algebra 2 and also a calculus teacher at our school likes to say is some old hippie caught another hippie tripping on acid. That's a little more interesting, I think. I honestly just stick with Sokatoa though. Sokatoa. You kind of have to say it with a little bit of accent, otherwise it doesn't quite fit the bill. All right, let's go on and look at some other ones because there's really 6 of these. All right, so these we call the reciprocal trigonometric functions, and that's really just because they're the reciprocal of the initial ones. It's 1 over whatever those things are. So this is cosecant, and then secant, and then cotangent. I don't know why 2 of them are cos and 1 isn't. I don't know. But cosecant is 1 over sine. Secant is 1 over cosine, and cotangent is 1 over tangent. These can be kind of tricky to remember which one's associated with which one, right? Oh, and then of course there's opposite over hypotenuse and whatever. Now, I remember secant because it's spelled like the opposite of cosine almost, right? So that's SEC, and this one is COS, right? So we kind of switch the C's and the O's. I don't know, that's my best guess. Cotangent's a little bit easier. And then I wrote over here, right, these are the reciprocal of the common ones, but you can derive these. By derive, I mean like you can create these. So let's look at just the cosecant theta. And theta is just what we use to mark any kind of angle. Instead of an X or a Y or a Z, we use theta. It's a Greek letter. It's kind of cute. So 1 over sine theta. Well, we should hopefully remember what sine theta is, right? Some old horse. SOH. So opposite over hypotenuse, or katoa. So that means I have opposite leg over a hypotenuse leg. Well, down in our middle school, they like to talk about keep changing and flipping. Or really dividing by a fraction or multiply by its reciprocal. So this is then the same as 1 times, right? Keep, and then I change my division to multiplication, and then I flip my bottom. So hypotenuse over opposite. And that gets me this one. Okay, so I personally would just remember sine, cosine, and tangent, and then I would make all of the other ones as I needed them. Alrighty, let's go on and check out an example. So sine, opposite over hypotenuse. Opposite of my theta is this 14. So 14 over my hypotenuse, which is 21. And then cosine, or kah, adjacent over hypotenuse. So my adjacent or next to side is 19. My hypotenuse is 21. Now tangent. Well, that's both of these on top of each other, right? Sine over cosine. And if we notice there, my 21s will cancel. I end up with 14 over 19. Now let's fact check this, right? Because toa is pretty easy. Opposite over adjacent. Opposite over adjacent. So 14 over 19. We got it. Once again, sine over cosine is the same as my toa. All right? Okay. Now cosecant. That, I like to line these up with each other. That might help remind you some stuff too. Cosecant, or this one, directly next to sine, is the reciprocal of that, which means, I'm just flipping these things, 21 over 14. Secant is the reciprocal of cosine, because they're almost spelled backwards. That's how I remember it. 21 over 19. And then cotangent, reciprocal of tangent, so 19 over 14. Awesome. This is all based on this triangle. Again, these have to be right triangles to be able to do this kind of stuff. Let's boot, scoot, and boogie to the next one. All right, so here I have one trigonometric ratio, and I need to find the rest of them. They gave me cosine theta equals 3 over 4, and they gave me none of my triangles. They just told me where theta was, which really doesn't matter either. If they don't give you a triangle, highly recommend you draw one in. It's helpful. It really is. All right, so cosine of theta is 3 over 4. What is cosine? Well, what does that ratio mean? Cosine, or caught another horse, or kah. So let's see, C-A-H, so adjacent over hypotenuse. That's my adjacent side over my hypotenuse. I'm then going to label my triangle. It's way easier for me if I actually label this stuff. That's a 4, and then adjacent equals 3. I don't know my hypotenuse, though. How can I find it? Well, it's the right triangle, people. Just Pythagorean theorem, clearly. Alrighty, so Pythagorean theorem. A squared plus b squared equals c squared. Well, what are all of these things? Adjacent, we'll call that a, because why not, right? 3 squared, I don't know my b. I do know c. C is a 4. Alright, so that means 9 plus b squared equals 16. Let's subtract 9 and subtract 9. B squared equals, oh, what is that, 7? So square root of that, big is square root of 7, plus or minus, but it's a distance, so it has to be plus. And I'm actually just going to leave it like that. So my opposite side is the square root of 7. I don't have a calculator on me, and I don't give my kids calculators most of the time anyway. So that's how I'm going to leave it. Go over to the right. I already know one of these. Cosine is going to be 3 over 4. And remember, secant is the reciprocal, or the flippiness, right, of cosine. So that one's going to be 4 over 3. Now that I know all of my sides, this is just the same as the last one. Sine, or soh, is opposite over hypotenuse. Opposite is square root of 7 over hypotenuse of 4. Tangent is toa, or opposite side, which in this case, remember my theta is up here now, opposite is over here, square root of 7. So square root of 7 over toa over my adjacent, or my next to, which is 3. Remember, theta can move around on you. It doesn't have to stay in that same spot for every problem. And then my reciprocals are pretty easy, right? 4 over square root of 7. And cotangent is 3 over square root of 7. Only caveat here. We don't really like square roots in the bottom, so we have to bring up rationalizing. This was way back for me, several chapters ago. But if we don't like radicals in the bottom, if it's a square root, we just multiply by that thing on top and on bottom. We do this when we're talking about imaginary numbers and all kinds of other stuff. So 4 times square root of 7 is just those two things right next to each other. 4 times square root of 7. Square root of 7 times square root of 7. That's now a normal 7. So I'm going to put that up here. There's similar thing is going to happen now with cotangent, right? So I end up with 3 square root of 7 over a normal 7. Cool. You ready? Let's go on to the next one. All right. We have some special triangles. We call them special. We have a 45, 45, 90, which is just a triangle with 2 45-degree angles and a 90-degree angle. And then we have a 30, 60, 90, which has a 30-degree angle, a 60-degree angle, and a 90-degree angle. Not bad, right? And let's go make these triangles, right? It's just way easier if you look at them. Here's my 45, 45, 90. Again, it has a 45, and a 90. But what are my missing sides, and what are the 6 trig ratios? Well, let's think about this logically with a little bit of geometry background. So one side is 2, one leg, not my hypotenuse, but both of these angles are the same. If both of these angles are the same, then both of these sides have to be the same. That's kind of the rule. So this is then 2. Well, then what does this side have to be? Yeah, Pythagorean theorem. You're right. A squared plus b squared equals c squared. So 2 squared plus 2 squared equals c squared. And that's a 4 plus a 4 gets me 8. Let's square root both of these. Last one was a 7, so this is as far as we went. This one's an 8. I can clean up an 8 a little bit. So square root of 8. Let me do a little factor tree. Where should I do it? Let's do it over here. Square root of 8 splits up into a square root of 4, a square root of 2. What is the square root of 4? You guessed it. It's a normal 2. Good job. So it's a normal 2 times the square root of 2. So normal 2 times the square root of 2 is what my c value, or my hypotenuse in this case, 2 square root of 2. Now that I have all of my sides, I can go and do those trig ratios. Might be some cleaning up, but we'll see what happens. So sine, or some old horse, or toa. Just love saying that. Toa. Anyway, sine is opposite over hypotenuse. My opposite. And remember, this is a sine of 45 degrees for all of these now. These are all 45s everywhere. All right, because I don't care about the 90. It's weird that way. I only care about that 45, and it's the same both directions, so it doesn't really matter. Opposite of one of them is a 2. Hypotenuse is 2 square root of 2. So let's sign that up here. So I have 2. It's my opposite over 2 square root of 2. That simplifies to a 1 over square root of 2. Dang. We don't like that, though, do we? That needs to be, and I'm running out of space, a square root of 2 over 2 when we rationalize. I'll show that down here at the bottom. So 1 over square root of 2. We multiply by square root of 2 over square root of 2. Gets me a square root of 2 over a square root of 4, or a normal 2. I'll skip that on the rest of them, just rationalize from the beginning. Cosine. Well, cosine of that angle is now adjacent, which is also a 2, over my hypotenuse. Oh, well, that's the exact same as the last one. So this also ends up being a square root of 2 over a 2. Now, tangent is toa, right? Opposite over adjacent, which is a 1. Sweet. Cosecant is the flippity flip of this, right? And I'm actually going to pick this one here, the one that's not rationalized, because then it just becomes square root of 2. And then this one, same thing, just a square root of 2. And then this one stays a 1, folks. 1 over 1, still 1. Ready? Are you? Let's go on to the next one. All right, so here we have our 30, 60, 90 triangle. And this, we'll think about it like it's an equilateral that we then cut in half, right? So an equilateral triangle where all the sides were 2, and then we chopped it down the middle. Okay, that's how we derive this one. And it's a 30, 60, 90 because it's 130 degree angle, 160, and 190 degree angle at it. So we need 2 different sets of sine and cosine tangent. We need ones for 30s and one for 60s. Oh, and I lost my parentheses on the last one. Don't worry about that. But we don't care about secant, cosecant, or tangent, or cotangent in this one. We're just going to do the main 3, but we're going to do it for each of those angles. So, first off, the 30. Oh, first off, actually, I only know 2 of these sides. I need to find out my other one. Because, again, it's an equilateral we chopped up. So, what's this height? Yeah, you're right. We need to use Pythagorean theorem to figure out what that thing is. So, I start off with my hypotenuse, 2 squared equals one of my legs, squared, plus my other leg, squared. Well, 1 squared is just a 1. 2 squared is a 4. So 4 equals 1 plus a squared. I subtract that 1 over. I get 3 equals a squared. Well, just like last time, folks, square root it. And my a side is the square root of 3. So instead of a, I'm going to write a square root of 3 over there. Sweet. Now we need to find sine of that. Remember? So, toa. So sine is opposite over hypotenuse, or some old horse, or some old hippie. Either way, it's opposite over hypotenuse. So what is my opposite side of 30? Be mindful of that. Here's my 30. Opposite of that is 1. Okay, what is hypotenuse. Almost said adjacent. What is hypotenuse? Well, that's a 2. And then what is cosine of 30, or my adjacent over my hypotenuse? Okay, so next to 30, don't pick the 2. That's the hypotenuse. It's always the hypotenuse. So which side is next to it but not the hypotenuse? Well, square root of 3. Okay. And then, hypotenuse is 2 still. And then tangent is these two things on top of each other, or my opposite leg, which is 1 over square root of 3. 1 over square root of 3, which we have to rationalize and get square root of 3 over 3. Okay. Now, let us do sine of 60. So now I don't care about that 30 anymore. I'm all about this 60. Sine is opposite over hypotenuse. So what's opposite of 60 now? Yep, square root of 3. And hypotenuse, still 2. Cosine, what's adjacent to my 60-degree angle? 1. And what is the hypotenuse still? 2. And tangent, TOA, opposite over adjacent. What is opposite of 60? Square root of 3, right? That is opposite of that angle. And then what is adjacent to it, or next to? And that's the 1. Now the neat thing is, right, the last triangle, this one, and this one, tell us a lot. Let me actually draw a little table for you. All right, so I have that table up here, and this is I think is really neat. So sine of a 30-degree angle is always going to be 1/2. Always. Sine will always be 1/2 of a 30-degree angle. And sine of 45 is always going to be square root of 2 over 2. Of 2. And sine of 60 is always going to be square root of 3 over 2. Cosine, a little bit different. It's actually the reverse of that. So cosine of 30 is always going to be square root of 3 over 2. Cosine of 45, well, still based on those special triangles, this one is going to be a square root of 2 over 2. Then we go down and look at our cosine of 60. It's going to be 1/2. So sine and cosine are opposites of each other. Sine is going to be getting bigger. Cosine is going to be getting smaller as we go down. The denominators of all 6 of these here are 2's. For sine, it starts going 1, and then 2, and then 3. Square roots of those things, though. But square root of 1, still 1. Then down here, cosine does the opposite. Square root of 3 over square root of 2, and square root of 1, or just 1. It's awesome that way. Then tangent, remember sine over cosine, or for us, a square root of 3 over 3. And then the next one's a 1. And then our last one, tangent of 60, is a regular square root of 3 on the top. No denominator on that one except the 1. So square root of 3 over 3, and then 1, and then a square root of 3 just on its own. Awesome, right? This table can be super helpful. I would encourage you to memorize this table. At least be able to draw it quick at the top of your paper and then keep going with it, right? Very helpful. Calculus, you'll have to memorize this thing. All right, well, let's go on to our next example. Oh, wait, we're done. Thank you for watching, everybody. Make sure you keep doing stuff carefully and with enthusiasm. Have a great rest of your day.